So here is a buzzword that you will have to get used to. Usually they are referred to as radiative forcing, but typically experts will just say forcing. For example, they will say human beings have become an external forcing. What do we mean? This directly relates to what we already talked about. So there is balance between incoming solar shortwave radiation and outgoing heat or long wave radiation, and anything that perturbs this balance is called a radiative forcing or just forcing. So when we say human beings have become a forcing, we mean that by adding greenhouse gases, by doing cement production, land use change, urbanization, deforestation, etc., we are changing greenhouse gas concentrations, and we are basically changing the balance of we're changing albedo, we're changing how much energy is absorbed, we're changing how much energy is going out, and so on and so forth. And we already implied that there are feedbacks in the system because we are evaporating water with the energy, we are forming clouds, clouds are reflecting or absorbing sunlight, they are sending out heat energy or absorbing heat energy from the surface, and so on and so forth. And I also mentioned in the very first podcast that if you think about weather during the day, once sun rises there is radiative forcing during the day, and sun goes down there is no direct solar forcing, and yet and there is seasons, of course. You are especially at higher latitudes, you have very strong seasons, and yet within a day weather can change many times because there are lots of these feedbacks: evaporation, condensation, clouds being taken around, changing the heating differently at night, differently at during the day, so on and so forth. So to cut the story short, we look at forcing delta F. So F is typically a symbol used for forcing, like in Newton's laws of motion. So delta F is the change in the forcing, which obviously is again radiative forcing. So there is a constant 5.35, which has units of watts per meter squared, is multiplied by natural log of C over C0, where C is, let's say, carbon concentration or greenhouse gas concentration when converted to CO2 equivalent and so on, divided by C0, which is a reference. So let's say at the beginning of the Industrial Revolution we were around 280 parts per million by volume, and we are now at 420 some. So the radiative forcing created by the greenhouse gases we have added till now is given by this. That is how we look at what is the net imbalance we have created and how that relates to the warming, and how the warming can be explained with energy going into the ocean, into the atmosphere, melting glaciers, and so on. Okay, so this is a way to look at it. Here we are increasing the ratio of C to C0. Radiative forcing delta F is shown here. So radiative forcing in watts per meter squared as a function of the atmospheric CO2 concentration relative to a reference value C0 according to that equation we just saw. Black straight lines indicate reference state C or C0 where delta F was 0, so that's your reference, that's why you use it as a reference. So let's say we are comparing changes in radiative forcing at 1850 or so. I'm just saying a number. We can say that's when carbon was the reference value, so that was 1, and that's when our delta F would have been 0. If we go before that, the carbon would have been lower over time, and we would have negative forcing, so there would be a cooling effect of taking out CO2. But as carbon dioxide increases, here green and red dashed lines indicate the current 2016 state relative to pre-industrial C or C0 of 400 ppm divided by 280 ppm, which is 1.4, or a delta F of 1.9 watts per meter squared. And if you keep increasing to double the CO2 with which we started at the beginning of the Industrial Revolution, then we are going to end up with about 3.7 watts per meter squared. So this allows you to say how much additional energy we are trapping into the system. And I mentioned before that 93% of this additional energy is going into the ocean. So that's the kind of thing we have to do to understand the rate of warming of the atmosphere, which is what we typically track. Okay, so that brings us to the greenhouse gases. So atmospheric methane concentration as a function of time. Recent air measurements from Mauna Loa. So the CO2 measurement started in the 1950s by Charles Keeling, but the methane started much later. So other thing to remember is that methane is in nanomoles per mole or in parts per billion by volume, as opposed to CO2, which is parts per million by volume. And you can see that it also has this seasonal cycle that was seen in the CO2. We will look at it again. And methane variability over time is not as easily explained because it depends on the sources and sinks. And the recent data has been added here, for example, from 2016 onward. Or 2019 onward. Methane comes from rice paddies, cattle, industrial activities, biomass burning, wetlands, and so on. So there are some changes in rate of change. There are changes in rate of increase of methane, which are yet to be understood to some extent. Okay, so looking at it again in context, there is CO2, which is very well mixed, long-living gas, so we can always measure it accurately and precisely. So we always do that. There is nitrous oxide, again in parts per billion, and an order of magnitude smaller than methane, which is also parts per billion. But again, remember, concentration, residence time, and global warming potential are the three things that matter. If we assume CO2 has a global warming potential of 1, methane has about 25 times the CO2 effect on greenhouse gas trapping or energy trapping, and N2O is, sorry, did I say NO2? N2O is about 200 times, and there are various CFCs and HFCs which are lived much longer or shorter and have much higher global warming potentials. How do we compute that? We'll come back to that later, but if you take a certain amount of CO2 and consider the forcing additional energy trapped by CO2 over a time, let's say 100 years, you compare the same amount over the same time for other gases like methane and N2O, and you see how much additional warming is created by these, and that's what gives us these factors of 25, 200, and so on. So global warming potential, remember, this is very critical. There are other things that matter as well for energy balance and feedbacks. These are the aerosols and other gases and smoke from the Australian fires. A nice animation put out by NASA. The satellites track wildfires, carbon monoxide, aerosols, clouds, water vapor, and so on. And animations these can be produced, and you can see the satellite tracks looking at these banded structures here. So let me leave this here, and then we will come back and look at the impact of volcanic eruptions. It turns out that volcanic eruptions are also an external forcing, which means what? We have solar energy coming in, heat energy going out. When you add energy that is not part of this regular system, like human beings digging up old fossil fuels, coal, gas, and oil, and burning it, then that greenhouse gas is essentially being added to the system as an external source. Volcanoes do the same thing. There is tectonics going on, and volcanoes erupt for various reasons, and they put out all the ash and carbon dioxide and methane and other things, carbon monoxide, etc., into the atmosphere again as an external source. So volcanic forcing also acts as an external forcing, just like human beings have now become an external forcing. So we have to consider fossil fuel burning, deforestation, cement production, urbanization, and all the other land use changes we make, industrial activities that add to greenhouse gases and radiation perturbation. and then we will look at the net of these including volcanoes, and try to see how much additional energy they are adding or removing to this the short wave long wave balance we introduced ourselves to. Okay, so fairly straightforward stuff, but the concepts are important. Make sure you listen as many times as necessary to make sure you understood it. Okay,